of East and Central Africa with power, because Congo River is one of the rivers with quite a large amount of water. So these are some of them from a global perspective. United States has got its own, but I think they do consume their power locally. They don't export to any country. In Kenya, we have been saying that we do not have enough, but I believe if we put our heads together and we decide to produce enough power to run our industries, we still have that kind of a capacity, because I've told you, Mutonga has never been touched, and others have never been touched. And again, when you look at the number of years where Sontumiriu was never thought of because of politics, yet it is one of the best river runoff systems that we have in East and Central Africa. Much of South Africa depends on what comes from rivers Abens, being shared by Zambia, Botswana, Malawi. I think they also use the same. And partly Mozambique. I think most of those countries rely on Kariba Dam for their power supply, and let me hope it is sufficient. I do suspect South Africa as a nuclear power plant. I suspect that because in the years of apartheid, they collaborated so much with Israel and other countries which are nuclear powered, and especially when it comes to power generation. It is one of the best you can ever come across. But the problem is, should there be an accident, my friend, the damage will be magnanimous, and it will take many years or many generations to correct a kind of a mess that will have been created. And that's why I do not advocate for Kenya going nuclear, because we are very careless and we hardly take responsibility for our actions. Okay? So this is a Three Gorges Dam in China, said to be one of the biggest. But I said Itaipu seems to be running it a close second if it is not becoming the first. And Igadam is also coming up on River Congo. Otherwise, I said the advantages of this is that the operating costs are very low. You have very few workers, engineers required to run the plant. But the plant, you find it can be very clean and very neat. And there is no smoke or soot, because everything apart from the noise coming from the turbines, everything else looks very okay, because you are using water which is running back to the river. You can also be able to meet the requirements of changing loads without any loss of efficiency with this type of plants. And the efficiency does not change with the time, unlike other type of plants. And no fuel is required for this. You don't need any fuel at all, unless you need fuel maybe for other things, or maybe you need to lubricate. So lubricants are not fuels. You need to lubricate some of the parts that are running, that is outside of the turbines. There are no standby losses, I can say that. Otherwise, land can also be cheaply available. I hope that is what they did in Nyakach, where Sondumerio stands. Though they still have, they had a lot of politics when it was coming up. Politicians told the community that you were given peanuts for compensation. And they almost refused that the project should take up. But they gave back to the community by building them a school. They also built them a library, which they hardly use. They gave them also free water. The people in Nyakach were given free water for irrigation by the Sonomirio project. But nobody is interested in that. Those guys are busy fishing and doing other things, growing mtama and those small scale farming, subsistence farming, instead of taking advantage of that free water from this kind of a scheme to grow food for export or for the market which requires food. Anyway, so much for that. How do we classify this, or what are the disadvantages of hydro plants? We said it is initial cost is very high, and availability of our power is not very reliable. Okay, since this depends on the quantity of water, then what would happen if there's a drought? And it depends on rainfall. What will happen is like what happened in Canberra one time when there was less water. Some of the turbines became cavitated. They experienced cavitation. And when I was there at that time, I found them trying to use stainless steel to weld back parts which were pitted or eaten up during cavitation. Okay? So it is harmful if there is insufficient water. And that's when you find people now resort to rationing. You allow water to rise up to a certain level before you can start generating power. I think it is almost the same thing which happens with Tuckwell. Tuckwell, they wait because Kerio River doesn't have a lot of water. They wait for the levels to rise so up so that they can start generating. Tuckwell was also supposed to be multi-purpose because it was supposed to remove cattle Lazarus from lacering so that they can engage themselves in useful agricultural activities. But I think nobody sensitized them on that. And that's why you find that the issue of banditry still rings out, even long after Sondomiriu. I mean, even long after Tuckwell was completed, sometime in 1992. Okay? Otherwise, it is one of the engineering masterpieces that you can ever come across. We used to go there with students, but security became an issue. We no longer want to go down there because even when we go for security, the Askaris were also being threatened. So we stopped going to Sondomiriu. I mean, it's not Sondomiriu, but Tuckwell, sorry. We classify these power plants according to the capacity of water. Okay? For example, we say Sondomiriu has no storage. Tuckwell has a storage during the high rains. And that's why I told you they have to wait for the levels to rise up. Otherwise, we can also do that according to the head of water available, where we have got low head plants. These have a dam across the river, okay, where you can impound the water. And once you impound the water, you can raise, or rather, you can generate power and you can generate power as per the requirements that you have. Otherwise, they can run 24/7 without stopping, except in the few small instances where you have to stop to check one or two things. Okay? Otherwise, we have medium head plants, which 30 to 500 meters of head must be available with a penstock provided also to take water to the turbines. Okay? Otherwise, at all times, we normally say with 200 to 400 meters as low and medium head, we can be able to generate power. Otherwise, we have high head plants where water is stored in a very high ground. Okay? And these ones you find the head is exceeding 2,000 meters. 2,000 meters for you to generate power. Then what kind of a turbine would you require? We shall get to that. Okay? So we have said for a site to qualify for layout of a power plant, Water must be available. That is number one, meaning you have to have a look at the rainfall records to determine the reliability of the rainfall. There must be facilities to store water, meaning there must be sufficient space and conditions that are essential for water storage. Then the head available, how high is the reservoir located? Can it provide enough conditions to run the turbines, and what type of turbines can be run with those kind of turbines? Otherwise, we mind about the load center where the plant should be situated where power is to be used. We don't do that in Kenya. We generate power around Gitaru because everything is sent to Gitaru. From Gitaru, we raise it to 132 kV, transport it to Nairobi. At Juja, we step it down to 66. Then at Ruaraka, we bring it down to 33 when we start sharing it out to the industries. Okay? That is what we normally do in Kenya. No wonder you find the ginger line. I don't know whether the ginger line still supplies us. It is still running, but all the power is brought to Nairobi, maybe the exception of what comes out from Kipevu. And then from Nairobi, it is now distributed to various parts of the country. I think we like centralization of so much, but it is also good to centralize because decentralization, you don't know what it may bring forth. The other thing is the site should be accessible where there is an access road or a railway, because these components or these tools or equipment for hydroelectric power generation, they can be too big. They are giant things. And when you carry them, there must be enough road to access the site where they are going to be installed. Okay? There must be enough, or there must be enough space to provide for roads and railways. If none of that exists, you may have to construct one so that you can facilitate, you can make a facilitation. Masinga Dam has benefited because the road from a town nearby has been tarmacked all the way up to where the power plant is. Kiambere from not Kiambere, yeah, from the main road to Embu, from Machakos County. So there's no question of the site not being accessible. Otherwise, when you are planning for a power plant, these are things that you should bear in mind. What are the essential components of bay? Then you may have a dam, if not just an impoundment like we have in Sonovirio. Look, then you may have to provide a surge tank so that you can be able to accommodate surge pressure. When you stop or when you are starting the turbine, you need water available, and you need also to dampen the waves that are, you need to dampen the waves that are generated when you stop the turbine suddenly, or in case there's power failure, or for some reason the thing comes to a stop. There has to be something to accommodate the backlash due to incompressibility of water, because it sends a wave back with a celerity faster than the speed of sound. And that has to be arrested, because with a mass oscillation being created, then the surge tank should be in place to absorb all that. There has to be a powerhouse where you put in your turbine and other accessories, and then we have the tail race, like I've said, where water from the turbine is disposed of. The point where you dispose of that water, it goes back to the river. That channel, we call it a tail race. And that's why I told you in Sonomerio they became clever. They decided to use the waters of the tail rays to produce 20 megawatts. They gave it to the Chinese, and they have it. They have actually made it possible to generate 20 megawatts out of the waters of the tail rays. Okay, they call it Sangoro. In summary, what are we saying? We have the head race, the tail race, okay? Or we simply have the tail race and the head race, whichever way you look at it. But you start off with the head race, then you end up with the tail race after the turbine. That is the tail race. Now, let's come now to the turbines in harness. What are they supposed to be? These are machines which are opposite of pumps because they convert what you call your kinetic energy, water, into and the potential energy into mechanical run, transformed, used now to run the industries. What are we likely to note with these kind of turbines? The kinetic energy of water depends on the mass and the head of water that is available. And that's why I told you we have a classification where we have low, medium, and high head plants. Okay? The potential energy we are talking of will always depend on the quantity of water that is available and the head that is available. Now you can imagine when there is a drought, what happens? What happens is that we have to close some of the outlets to raise the water level up to a certain standard. Then from there, you can be able to generate power for the consumers. Okay? Otherwise, turbines will require large quantities of water, some at high heads, some at medium, and others at low heads. So we say that they require large quantities of water. We may also have some which may require small quantities of water, but they can be very expensive. Though, when you look at what they do, we may say that the end justifies the means. Okay? What of large quantities of water? We have to select a turbine which will be commensurate with that kind of a condition available in a site. Okay? There is likely for that to happen. What of when we have small quantities of water, it will require low quantities, but also with low heads, up to 5 meters, we can be able to generate power. Okay? Otherwise, that is now what these turbines are capable of doing. Now, how do we classify them again? We can classify turbines on the basis of the action of water on the moving blades. Yes, we can classify them according to that, just like we did for pumps. The only difference is that they do not bear the same kind of a name. Otherwise, for this, we have two basic types of turbines. We have what we call the impulse turbines. Please note that. What about the impulse turbines? With these types of turbines, they take the whole of pressure energy in the turbine and it is converted into kinetic energy. Yes. impulse turbines, you take the whole of energy in this turbine and it is converted into kinetic energy. That is for impulse turbines. What of reaction turbines? These ones operate on the difference of pressure at the inlet and outlet of the turbine. Let me say they are a special case because they are some of the most efficient and some of the most widely used types of turbines. We'll be able to see that as we move along. Now, turbines, though they can be classified on the basis of action of water on the blades as impulse or reaction turbines, we can also name them or we can classify them in accordance with the name of the originator of the type of turbine. Number one, we have what we call the Pelton wheel turbine. This one was invented by engineer Lister Pelton. Okay? He came up with one of the best turbines that you can ever think of. Yeah? Then we have what we call the Francis turbines. The inventor of this was Francis, and it is one of the most efficient turbines that you can be able to come across. Then you have the Kaplan turbine. This was invented by Victor Kaplan, not Victor Desmond, but Victor Kaplan, okay, from Austria. In fact, when I went to the Technical University of Vienna, I went to their Hall of Fame and I wanted to see where they have placed the name of Victor Kaplan, who gave the world one of the best and one of the most efficient turbines you can ever come across. Yeah? I also wanted to see names of people like Casagrande, because some of those people you quote in soil mechanics, they all came from Austria. They were Austrians, no, they are Germans. They did a lot of good work. Okay? Kaplan turbine is one of the best you can ever come across because it can operate at a very low head, even up to 5 meters. At 5 meters, you can run it and you generate power enough to supply maybe an industry or several communities. Then last but not the least, and not so highly acclaimed, we talk of the Thomson turbine. Okay? So that is now the second way of trying to classify these turbines on the basis of the name of the originator. The first one was the action of water on the moving blades, where we had the impulse and the reaction turbines. Then number two, on the basis of the name of the originator, where we have the Pelton wheel turbine, we have the Francis, we have the Kaplan, and we have the Thomson. Thomson, we just mentioned it, though we may not lay a lot of emphasis on what it can do and its capabilities. On its capabilities. Number three mode of classification is we can classify turbines on the basis of head and the quantity of water available. Yes. We can have high head turbines where we operate at 200 meters when you are using small quantities of water. And a good example is an impulse turbine represented by the Pelton wheel. Okay, I know the Pelton wheel may be said to require small quantities of water, but when I see how the operations of the Pelton wheel are, I've never been convinced that it requires small quantities of water. Then we have the medium head between 30 to 200 meters, which require medium waters. Okay, and we say they require medium reaction. They are actually medium reaction turbines. And a good example of that is the Francis turbine. If we are called Francis, don't think it is your turbine. It is not. Last but not the least, we have the low head, which are below 30 meters. And we have medium head between 30 to 200 meters, requiring medium quantities of water. Okay, and a good example I've said is a Francis turbine. Otherwise, for the low heads, they operate below 30 meters. But the funny bit is that they require large quantities of water. This is a reaction turbine, and a good example of a low head is the Kaplan turbine. Any questions on that? Any questions before we move on? Okay. Still on the classification of turbines, we can classify them on the basis of the disposition of the shaft. Turbines either have a horizontal or vertical shafts. But speaking generally, it is the Pelton wheel turbines that have horizontal shafts, while the Francis and Kaplan turbines have a vertical shaft. Okay? Pelton wheels have a horizontal shaft, but a Kaplan and a Francis turbine have vertical shafts. So that is another mode of classification on the basis of or disposition of the shaft. Now, we can also classify them depending on the direction of flow of water in the runner. We'll have to dissect a turbine so that we can tell ourselves what the runner is and what the vanes are. So we can classify them on the basis of direction of flow of water in the runner. Just like the pumps, you may have radial flow turbines where the flow is in radial direction, either inwards or outwards. Otherwise, we also have tangential flow turbines where water strikes the runner in the direction of the target. And a good example of this is the Pelton wheel. You'll be able to see details of that. Okay? Then we have what we call the axial flow turbines, where water enters the runner and leaves in a direction which is parallel to the shaft. And it is for that reason we refer to them as the axial flow turbines. Okay? We refer to them as the axial flow turbines. Then we can have what we call mixed flow turbines, where water enters radially and it leaves the runner axially. You may have that kind of a condition. We'll find out whether we have a good example on that. So these are types of turbines that exist under those classifications on the basis of direction of flow of water. Okay. Then we can go further to classify turbines on the basis of the specific speed. Okay. Remember, we defined speed for pumps. And we said specific speed is the speed of geometrically now similar turbines, not pumps, to develop 1 horsepower under a head of 1 meter. That is how we define specific speed of the turbine. Geometrically similar turbines to develop 1 horsepower under a head of 1 meter. Okay. We have good examples of that, where we have the Pelton wheel running between 10 to 35 with a single jet and 50 maybe with a double jet. Otherwise, we have the Francis turbine, which has 50 to 300. Yeah. Then we have another one. Here we have the Francis turbine running between 50 to 300. And when we talk of specific speed, sometimes we may express it in dimensionless form. And then we have the Kaplan, which could be RPMs, but it is for the specific speed. So we can classify as a power plant. Through the dam, you have the penstock, an arrangement, I'll call it just as Lewis. Then you have the turbines, which releases water back to the downstream. And because it has a vertical shaft, it could be a Francis or a Kaplan. The vertical shaft is linked to the generator so that to produce so much, you step it to a grid and you can now distribute it wherever it is required. Here we have the various types of turbines on the basis of the originator. We have the Pelton wheel, we have the Francis, and we have the Kaplan. Okay? You can see from the vertical shaft on what I have in the first diagram, that could be what? Is it a Francis or is it a Kaplan turbine? It is more like a Kaplan than a Francis turbine. Okay? Then you have the arrangement down there of head race and the tail race. We have what they're calling the penstock. I would call it the tunnel up to a certain extent before I can be able to reach the surge tanks. Then from the surge tanks, I have what I may not call a penstock. Otherwise, it is hand with a nozzle so that whatever comes out of the nozzle can hit on the vanes and facilitate in rotating the turbine. And this is more so for a Pelton wheel. Otherwise, we may have a Francis next to the Pelton wheel with all those kind of details. I think the best thing we can do, or the fairest thing we can do about these turbines is, and especially for clarity, let me see. Uh-huh. Especially for clarity, am I doing the right thing? Yeah, let me do the right thing. Yeah, what I mean is that I'll remove this and then I'll bring one of these here. I'll bring one of this, which I've said it is more of a Kaplan. It is more of a Kaplan turbine than another. Okay. Yeah. Let's say there we are with, I believe this is a Kaplan. Kaplan turbine with its vertical shaft. That's what I wanted you to see. I wanted you to see the starter, the rotor, the turbine generator, and the water flowing in, the wicket gates, which are several, and the turbine blades. This is actually a Kaplan turbine. Then after we have seen that in that version, let me see whether I can create space for another one. And which is this other one? Let me have the layout for the Pelton wheel. I think I should have deleted this. Let me cut it so we can have it here. Okay, I can have it here, blow it up so that you don't miss out on this. Should be able to see this clearly with all the details. With all the details where you can be able to see the penstock, the head, yeah, the dam, the penstock, the head, the nozzle, the tail rays, the turbines, and the vanes, and gross head available. to the gentleman by the name Victor Desmond Tutu. Okay. I know there are some which never came. I'll see how I can split them so that they can be able to reach you. Otherwise, I'm glad we are moving towards a good position. LNS turbines or turbine types. I think that's better. Turbine. And it said, Dear Desmond Tutu and Company, please find this. Please find that and let me attach it. Call them turbines. Okay. Let me believe it's all right. Mhm. So that goes to Desmond. As we say, it has been sent to Desmond. From there, let's get into more serious thing, turbine 2. Okay. I don't know why I'm starting with this turbine 2, because I would that I start with the Pelton wheel turbine. Let me see whether I have it in isolation. Yes. So let me start from here. Much of this, you have seen it in the preamble about the layout, about the plans and their classifications and all that. And then we talk about the Pelton wheel. The Pelton wheel, I told you that it is an impulse turbine, and this was by engineer Lester Pelton, 1800. These type of turbines operate under very high head, up to 1,800 meters. But the beauty of them is that they require small quantities of water when you compare them to the others. Such that from the head raise in the mountains, water is conveyed to the turbines in the powerhouse through, or from the powerhouse through the penstock. When you look at this type of turbine, the lower end of the penstock usually ends up with a nozzle. And it is this nozzle which is used to direct the water oozing out of the penstock to the blades of the turbine. This type of turbine has got buckets that are mounted on the periphery of the circular wheel, and it is them that are known as the runners. Yes. So they have buckets mounted on the periphery of the circular wheel, or else you may refer to them as runners mounted on the periphery. And unlike other types of pumps, they have a shaft. They have a shaft which is horizontal. The other thing is large quantities of water. Then there is a number of buckets which are mounted on the periphery so that when the jet hits the buckets, then it forces the wheel or the runner to turn on the shaft, which is connected to the turbine, not the turbine, but the generator. And thereby we generate power, which is to some quantities. Then thereafter, the power is stepped up to the national grid so that we can be able to transport it. In fact, if you look at most of the plants, they generate 11 kVs, but we end up raising it up to 132 kV, the national grid. If you look at the Kaplan turbine, the way it was designed, it looks clumsy, okay? But the beauty of it is that it requires very small quantities of water to be able to run it. Otherwise, whatever amount of water comes out of the nozzle, which is at the end of the penstock, it is actually controlled by a regulator, or what we call a governing arrangement, in the case of some of the big installations of these turbines. Otherwise, we can say the impact of water on these buckets would cause the runner to rotate. Okay? Thereby, you develop mechanical energy, which later generates electric power, which we are in need of. Otherwise, after the work is done, then after the work is done, the water is discharged back to the river through what we are calling the tail race. We still have this kind of a layout, which we have done seen, and we also have this, which we have done seen. We have this as a general layout where you can plan your power plant. Otherwise, we have seen all this. We have seen all these classifications, and all this, we have gone through all this, because that's a repeat. Then this is the guy, or the Pelton wheel turbine. You can see the shape of the inlet, which ends up with a nozzle. The nozzle is also coupled with a rod spear, to make sure that you create a jet which will impinge on the buckets. Once they impinge on the buckets, then you can be able to rotate the buckets, or rather you can be able to rotate the runner, which in other words, we can say it is its impeller, but will not use the word impeller in this case, like the pump, like in the case of pumps. We are going to use the term runner for the turbines. Okay? Water after hitting the buckets will discharge down so that it can be able to join the rest of it as it goes through the tail race and then back to the river. So these are the component parts. You have the buckets, you have the nozzle, you have the spear, you have the spear rod, and it has a deflector to make sure that the jet is deflected to hit the buckets and hit the buckets properly. Here you have more details of the same. And this is where we say that the Pelton wheel being an impulse turbine, it must run at atmospheric pressure. And it is for that reason that it is located above the tail race. Yes, it is located above the tail race, because when you see where it is positioned, the tail race is below where you can see the water level as water finds its way back to the river through the tail race. The buckets are shaped in a manner that water will enter tangentially in the middle and discharge backwards and flow again tangentially in both directions. And by so doing, you can avoid thrust on the wheel. In this case, you find that the jets are deflected by an angle of 160 degrees. And now you can see the placing of the runner, the buckets, and the casing to avoid the splashing of water. You can see the jet with a deflector, and you can see the spear. Of course, the spear has a spear rod. As the jet impinge on the buckets, water flows and joins the tail race as it goes down back to the river. On the right-hand side, you have details of the bucket, the way it is shaped. That deflect, or rather, it can be able to facilitate once it is impinged, and then it can have power to rotate the runner. That is its elevation. You can see it on plan, and also you can see the side view of the same. Okay, this is purely for a Pelton wheel turbine. Okay, and those are the component parts of a Pelton wheel turbine. Here you have the same guy holding up in another shape, in another format. It looks very ugly, but it's a beautiful piece of thing. When it comes to power generation, though it requires high heads, but very little amount of water is required for this. Here we have its installation in a powerhouse, so that when you open the casing, you can see the runners mounted on a shaft, so that the gentleman, after he finishes what he's doing, he can close the runners, allow water to come through, and you can generate power. Still another form of it, you can see, more detailed. You choose what you feel is good and easy for you. Still have more details of the Pelton wheel. Or to have a look at the functions of the nozzle. The nozzle is one of the major components of a Pelton wheel, and it is placed at the end of the penstock. It is here where you find pressure energy which passes through the penstock, which is a pressure conduit, is converted into kinetic energy, and it is further increased by provision of the nozzle. Yes. But all that is happening under the influence of atmospheric pressure. Otherwise, water flowing will strike the buckets that are fitted on the periphery of the runner to produce mechanical energy. When it comes to operation of small turbines, you may use a single jet, or a single jet is ideal for that. But for a large turbine, you may require a number of jets to run the wheel. Okay? So water will strike the buckets fitted on the periphery of the runner, and that way you produce mechanical energy, which after rotating the shaft should be able to produce electric energy. Let's talk about the spear or the needle. Now, this one you come across it generally around the nozzle. Okay? You generally find it around the nozzle. Okay. The needle, if you look at it carefully, it is so shaped in such a manner that as water comes out of the nozzle, should be able to actually redirect it to hit the buckets, and by so doing, we can be able to rotate the runner. You can see in the figure which is on the right, that single bucket. You can see the runner, you can see the spear rod, you can see the position of the nozzle, or directed to hit the runner without spreading the waters further. All this will run and water will flow out from the nozzle, or will allow water to flow out of the nozzle depending on the varying demands of power. Okay? Then here we have the buckets. They are so shaped like a hemispherical cup, divided by a common dividing straight edge, where the jet impinges. And when the jet impinges on this kind of a cup, then it forces the runner to rotate. Okay? And that's why we say that the jet will divide itself into two parts after sliding over the inner surface and turning through 160 to 170 degrees. It leaves the outer edge of the bucket. Okay? And that's why you can see the elevation of the bucket, the plan, and the side view. Now, these buckets are made of cast iron. They can be made of cast steel, or if need be, they can be made of stainless steel, of which we know if they are made of stainless steel, they are likely to operate for so long or run for so long without getting rusted. Otherwise, if you look at the inner part of these buckets, it is so shaped, if not polished, to minimize what we may call friction. And at this point here, we may not go to the details of checking how friction is not allowed or it is minimized in this kind of a system. So component number 3 is the casing. Number 2 was the bucket. Number 1 was the nozzle. The casing has no function, which is very serious, in the impulse turbine. Otherwise, they are provided to ensure that they prevent splashing of water. If you look at this, you see the casing? It covers the whole setup, meaning when it is in operation, there should be no splashing of water. Even in this case, you can see where that gentleman is. He has maybe lifted or removed the cover for servicing. Otherwise, they're supposed to have the cover. Okay? You should be able to place back the cover, which should be there, so that the turbine wheel or runner can move with ease and without splashing water. Number 4 component, okay, after the casing is what we call a hydraulic brake. The use of that is to ensure that we can be able to stop the running of the turbine. Because you find even long after you have stopped, supplying water to impinge on the caps, the turbine will continue running. And what is it running against? You have to be very careful. And that's why we have to stop it. Because someone could be working on the other side and it is running, generating power. And that's why we have to come up with a brake to stop that kind of a movement. So it is for that reason we say the brake nozzle will issue in a direction opposite to that of the rotation so that we can make sure that we have stopped the running of the runner or the wheel. Otherwise, appreciate the presence of the spear, the deflector, the nozzle, and the jets that are being struck by the nozzle. All these are component parts of a Pelton wheel. You can also see the position of the brake nozzle. Okay? Here you can see the details. Then after we have seen now the details, let's get to the crunch of the matter, Mr. Omondi Collins. Any questions? Any questions on this? Any questions I'm asking? Or you have not got the words? Please make sure you catch the words. I will share these notes, don't worry. But you should understand the running of these turbines. Okay, the Pelton wheel. Now, we have to look at the inlet and outlet diagrams of the Pelton wheel so that with the inlet and outlet diagrams, we can be able to compute certain things concerning the Pelton wheel. And this is where you have almost nothing on the inlet diagram. As I said, a turbine is the opposite of a pump, which just receives. So we more or less like have what we may call the outlet diagram. When you look at that diagram, V is equals to VW, which is the velocity of the horizontal jet. And the U is the peripheral velocity of the bucket at inlet, while D is the mean diameter of the pitch circle of the turbine, or the pitch of the mean diameter of the pitch circle of the turbine. VR and VR1 are the relative velocities at outlet and inlet. can see VR, can see VR1, okay, V and VW and U, where now VFL is the velocity of flow at outlet, or VF1, not VFL. We call it VF1, okay? Or else we have VW1, which is the wow velocity. At the outlet, you can see the positioning of the VW1. VR1, VF1, okay? And we have VR. Then U and we have V is equals to VW. Okay? VW1 is the wow velocity at outlet, while U1 is the peripheral velocity at inlet. Yes. Then U1 is the peripheral velocity at outlet, so that U1 will be equal to U. Since the inlet and outlet tips of the buckets are the same distance from the center of the shaft, that is what we are saying when you look at that diagram. Let me believe you are very comfortable with this. It is simpler than what we have had before for the pumps. Now let's have a look at the working of a Pelton wheel. As the jet impinges the buckets. Remember V1, VW1 equals to V1 for the inlet triangle. We have V1, we have got U, and we have VR1. And you can see the way in which the nozzle hits the buckets. And when it hits the bucket, the kind of a motion it puts it into to rotate. Okay? You can see that. Otherwise, for the inlet velocity diagram, we say water will enter tangentially. And therefore, the inlet velocity diagram is simply a straight line. And that's why they differ with what happens when it comes to centrifugal pumps. Okay? Alpha equals to 0 in that case, and theta equals to 0. While VR equals to V minus U, and the VW is equals to V, which is equals to the square root of 2GH. So simple, unlike working of the pumps. Well, whatever head is available at the nozzle will be equal to the gross head minus the losses in the pipeline, and this will lead us to V equals to CV V is equals to CV by square root of 2GH. I'm sure you are familiar with that. Otherwise, looking at the diagrams, the inlet and outlet, what can you be able to see? And that's why I was saying it is simpler than what you are likely to have interpreted when it comes to centrifugal pumps. Okay, having seen that, what is the next thing? Referring to the outlet velocity diagram, we say water will pass over the curved surface of the bucket. And for that reason, VR1 becomes less than VR due to friction losses. And therefore, we can say VR1 equals to a constant K times VR. And for generalities or for general purpose, the friction losses in this case, they are neglected. And you take K as a unit. Otherwise, VR1 equals to VR. VR1 equals to VR. And the VW1 equals to VR1 cos phi, which is equals to, or cos phi minus U. So what is the amount of work done? This will be equal to U by G into V minus U plus V minus U cos phi. That is the equation which links that. We have VW1 is negative as already discussed. That is what we can say. And the amount of work done by the Pelton wheel, we can say that will be equal to wow velocity VW by U by G plus wow velocity 1 by U1 by G, and we shall express that in kilograms per second. But remember capital U. Let me use capital U. This will agree to be. We hope I can manipulate this. So capital U equals to U. Therefore, work done is equals to VW U by G plus VR cos phi minus U upon G by U, which is equals to V times U by G plus V minus U cos phi minus U squared by G, which is equals to U, I don't know whether you can remember this, by G by V minus U in brackets plus V minus U in bracket cos phi. Okay. And that is equals to U upon G into V minus U into 1 plus cos phi. From this, we can be able to divided by the kinetic energy of jet per second. And therefore, we can say hydraulic efficiency, eta H, equals to hydraulic output upon hydraulic input at nozzle base, which is equals to V squared minus V1 squared by 2G. Yes. All that upon H. And therefore, hydraulic efficiency will be equal to U upon G into V minus U in brackets plus into brackets 1 plus cos phi upon V squared by G by 2G, which is equals to the next equation where you have 2U into V minus U into 1 plus cos phi by V squared. So hydraulic efficiency equals to shaft horsepower divided by the horsepower of the wheel. Okay,